तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have seen until now pressure measurement and the vacuum measurement. Vacuum measurement, we know it is again a pressure, it is a low pressure than atmospheric conditions. So we call it vacuum. So it's again a pressure measurement. Vacuum is pressure measurement. So whatever the technique we used for the pressure measurement, we can use it for vacuum measurement also. For example, Bourdon gauge and bellows, diaphragms. If you put the one side, for example, if you take Bourdon tube is there. This is what you have seen. If we can put this the atmospheric conditions into a casing, and this you evacuate. If you evacuate the surrounding in which the Bourdon tube is put, then Bourdon tube itself can measure the low pressure or vacuum pressure. Similarly, a diaphragm, when we see when we have got diaphragm, and this side if we say P is equal to 0 vacuum, and here it is some pressure Pi vacuum pressure, then you will find we can measure the vacuum pressure also lower than atmospheric conditions. So the Bourdon tube, the pressure, the diaphragm or the bellows can also be used to measure vacuum of low and moderate values. Other methods we have seen in detail last class, that is McLeod gauge and viscous vacuum gauge and Pirani gauge and all other methods. Otherwise, we can whatever method we used for the pressure measurement we can use it, provided the surrounding in which the instrument is there is evacuated and absolute pressure is vacuum pressure is applied inside the tube. That way we can measure it. Today we are going to see another one, sound measurement. Sound is also a pressure, because what is sound? It is a mechanical disturbance taking place in the air, or liquid or in solid. Sound can be propagated by any one of these medium, air, gas, or the liquid or sound or the solid. These three can transmit sound. What is actually sound? When we say light is electromagnetic wave, light, whereas sound is mechanical wave. When we got a source, so this is a source, source, it will produce, if it produce some sound, that means the nearby molecules, I mean any mechanical vibration having a frequency of with the frequency of 20 hertz to 20 kilohertz is there, then the sound is produced, because sound frequency is 20 hertz to 20 kilohertz. Suppose we vibrate, now what I am vibrating is 1 or 2 hertz, that is all, so no sound is there. But if I can vibrate at 20 to 20 kilohertz in that frequency, naturally sound is made. That sound is propagated in air. How it is done? When movement is there, the nearby air molecules are compressed, and then when the movement is away, then the air molecules are rarefied. So you find alternatively compression and rarefaction of air molecules takes place around the sound producing source. So that waviness is produced, is maintained, and it is propagates through the medium of air or the gas or liquid or solid. That is the propagation of sound. Now we are concerned here the measurement of sound. It is because we consider sound as here sound measurement mainly refers to noise. that is noise is unwanted sound. Unwanted sound is noise, and when we like that sound we say music. When music is frequency is particular or in slow step variations, slow variations, not sudden variation in frequency or tone. When there is all sorts of variations in frequency and tone, then such a sound is unpleasant, and then we call it noise. Noise is a public nuisance. Why? When there is a noise, I have to shout over the noise, or when somebody talks, he has I cannot hear because there is some other disturbing source. So that means my hearing power, hearing is disturbed by the presence of some other sound. So we know it is a public nuisance sound, and these noises, and in order to reduce such noise, engineers take many efforts while they design the equipment. And we might have noted in newspapers advertisement of a typewriter, noise free typewriter, electronic noise free typewriter. A mechanical typewriter, we say for that one better feature is, one good feature is less noise. This typewriter makes less noise, like that. So noise free machines, noise free apparatus have got, that is a special specification for many things. So while we design an instrument, naturally we have to see that noise is reduced to the extent possible. So naturally, whether noise is reduced or not, how do you know? Unless we measure the noise, we cannot we cannot specify or quantify the noise. That is what we are learning here, how to quantify noise. So for that we have this unit, sound pressure level. Sound pressure level is unit, simply it is called SPL. It is defined as 20 log to the base 10 P by 20 decibel, where P is in micropascal. That is RMS variation of the we know how the sound varies. Sound has got all these frequencies. So when we talk, the frequency of sound is varying, and that means this is atmospheric pressure. This is atmospheric pressure. So the atmospheric pressure will varying when there is a compression. This is rarefaction. All these variations, random variations within the frequency of 20 Hertz, 20 kilohertz is taking place. This is the pressure variations. This RMS value of it, root mean square value of it, that value, that is P is in micropascal. That value is 20. That value is to be substituted here, and that is at 1000 micropascal at 1000 Hertz. That is a reference frequency, because the 20 represents 20 micropascal at 1000 Hertz represent the threshold of hearing. It is called threshold of hearing. What is threshold of hearing? The necessary pressure to make us hear any sound. If the sound is less than 20 micropascal at say 1000 Hertz, then we cannot hear. That is the capability of our ear, human ear. So if the P produced by a source is equal to 20 Pascal, log 1 is 0. That is, it is just when 0 decibel means it just near about our capability to identify sound source. Anything more than that, we take the logarithm scale. Why do we take the logarithm scale? Logarithm scale normally adopted when the range is very large. We suppose the range is say 10 to the power of 10. Can we take can we have a linear scale to represent 1 to 10 to the power of 10 units? Even 1 to 1000 units means it's very difficult to represent in linear scale, and 10 to the power of 10 definitely we cannot represent in linear scale. So in such cases we go for the logarithm scale. Actually we find that what is the range here? 20 micropascal is that is 20 into 10 to the power of minus 6 Pascal. That is the lowest value it measures. And what is highest value? It is nearly about the threshold of pain 140, rocket engine, and atmospheric pressure is 194. That is equal to 10 to the power of 5 Pascal. Atmospheric pressure is the scale range, it varies up to 10 to the power of 5 Pascal equal to 1 atmospheric pressure. That means what is total range? Say it is a 10 to the power of near about 10 to the power 11. This is the range. 1 to 10 to the power 11 units to represent in linear scale is not possible. So we go for the logarithm scale. So the sound pressure level is always measured by this SPL defined by 20 log P by 20 decibel, where P is the sound variations in RMS. This RMS means you have to square it and then take root mean square value. this is variation on both sides. So that is a pressure, sound pressure. So in a sense, we are supposed to measure the variation of sound measurement means the pressure measurement, how the pressure varies around atmospheric pressure, around atmospheric value. That is what we are going to measure. That's why we are learning sound measurement along with the pressure vacuum. Also we are measuring this. And some of the values, SPL, decibel, sound pressure level for in decibel for known sound sources are tabulated here. Soft whisper, when two people sit nearby and whispering some information, and if we measure to 2 meter distance, the distance is important. When you measure sound, at what distance you measure sound is important, because longer the distance, sound level, sound pressure gets reduced, sound is reduced. It is inversely proportional. Suppose if we double the distance, then the sound pressure is half of the earlier pressure. So that is the case with the sound. Also it is stated, we have to, this is inverse proportionality. It's called inverse proportionality. Inverse proportionality of sound. That is there if we measure if we have the distances, minimum distance is 4 times minimum, 4 times the dimensions of the dimension of the source. Yeah, suppose a typewriter say 1 foot in length, then 4 feet away from 4 feet, later on we can measure the distance. Within the 4 feet, we find it is not observing this rule of inverse proportionality. What is inverse proportionality? That is, sound pressure will be inversely proportional to distance. That is not valid when we are measuring too near. That is one aspect of sound. Second aspect is when we have a sound making body and it is not making equal pressure in all directions. In certain directions it makes a larger pressure than the other direction. That is called directional property of sound. This is the directional property of sound. This is both the things, inverse proportional of sound and also directional property of sound, will be valid only when we measure the sound in an open space. There should not be any nearby wall. If there is nearby wall, what happens when the sound is made by one object, that we are measuring sound herein. We are measuring the directly coming sound as well as the sound comes and falls here and reflected. That sound also we will measure. So when there is a reflecting walls nearby, then that sound also is measured, reflected sound also measured along with the original sound from the source. So we should when we make the sound measurement, we should be careful that nearby there is no wall. Under this situation only these two rules are valid. So that's why in many places we find the sound, what is the sound measurement distance for sound is also given. Soft whisper, when it is measured at a 2 meter distance, then it is 35 decibel. Then small town residents, general noise in a small town will be around 45 decibel. In urban residents like Madras or Madurai, big cities, you will find a lot of movement, traffic and all. We find 50 decibel is the average sound level. Then auto at 100 kilometers per hour running at 3 meter distance, if you measure 65 decibel, mechanical typewriter 75 decibel, the heavy truck lorry with loaded lorry at 15 meter distance, if you measure 85 decibel, and pneumatic chipper, because pneumatic will make lot of sound, 140. What is threshold of pain? If the decibel is around 140 decibel, if the SPL value, then your ear starts paining. That paining value is 140 decibel. And we find rocket engine, when it takes off, it makes 170 decibel. That is the reason the scientists are housed in a closed housing with glass windows, so that they can observe the taking off of the rocket as well as their ear is protected. Otherwise, it is more than 170 decibel, more than the threshold of pain. Your ear will go away in no time. So that is very important. Atmospheric pressure are 194 decibel. So these are the rocket engine. Another point is rocket engine pressure is so high. Sometimes the rocket panels fail due to fatigue stress produced by the sound at the time of takeoff of the booster rocket. So sound, you cannot neglect it. Sound produces some even failure of some parts. So measurement of sound is very important. And the instrument used to measure the sound is called sound level meter. It is here. It is sound level meter. That instrument what we use to measure the sound is sound level meter, and it is made up of some basic important units I have put here, that is in signal flow diagram. First we have got so called microphone. Mic is one, that is what I have here also, it is mic. It converts the sound into electrical voltage. What is sound? Sound is nothing, pressure variation, we already learnt. This pressure variation of this what I have seen earlier, this pressure variation will be of this nature. This is the pressure variation around the atmospheric pressure, and it converts into voltage variation of the same nature. So voltage variations, pressure to sound, that all what it achieves the microphone, and one or two versions are there which you will see little later. As far as now we will say microphone achieves the changeover of pressure to, or transduces pressure variation into voltage variation. Then it is amplified, that voltage is amplified because it may be very weak, it amplifies. Then we call so called weighting network. Weighting network is an important unit in any sound level meter. We have got three scales, A scale, B scale, C scale, and another one is flat, which doesn't belong to any one of these things. See what the weighting network importance is, the loudness is different from loudness. Is different, is a function of, loudness is a function of SPL and frequency hertz. That is important. See we have got equal loudness curves. See the loudness phenomena can be explained with this equal loudness curve. Here we say A scale has got 40 decibel SPL value at 1000 hertz. Such a tone is called A weighted network, and a little higher loudness, say 70 decibel at 1000 hertz, we call it B scale, and 100 decibel at 1000 hertz. Any noise, any sound has got such a decibel at this 1000 hertz, they are grouped under these three scales, A, B, C scales. Most of the research purposes we go for the A scale. So anyhow, these are the three scales available in any sound level meter, or we can specially order a meter only with A scale also, that is also available in the market. In the A scale, the sound or the loudness made by 40 decibel at 1000 hertz will then another sound having 20 hertz frequency making 90 decibel SPL value, both of them, that 40 decibel at 1000 hertz and 90 decibel at 20 hertz, both will have the same loudness. That is why it is called equal loudness curve. So say for example 100, suppose it is 100, then 60 decibel. 60 decibel at 100 hertz will make say a noise equal to 40 decibel at 1000 hertz. That is why I have put loudness is a function of SPL and the frequency. So what we are measuring in this sound level meter is the loudness. So if SPL alone is obtained according to our definition, 20 log to the base 10 P by 20, that is not sufficient. We should you see, after all, a human being only is judging the noise source, and he will judge only based upon the loudness. The loudness of the machine. So loudness is important for our comparison of the machines. So naturally, the weighting network brings the value of the SPL to the loudness. How it does? It has got so the attenuation of weighting network. What it does, suppose so noise has got 20 hertz and that noise is making 90 decibel pressure variation, then what it will do, since it is equal to 40 decibel at 1000 hertz, it will subtract from 90 that 50, make it 40. So that loudness is seen in the indicating meter as 40 decibel loudness, because that is equal to 90. So what it does, it subtracts 50, that is attenuation. What it attenuate at 20 hertz, whatever be the pressure, whatever the SPL value, from that it will subtract 50 and indicate the remaining value. That means if it is 90 decibel at 20 hertz, our meter will show and only as 40 decibel. It is because that loudness is equal to loudness of 90 decibel is equal to loudness of 40 decibel at 1000 hertz. So it will show 40. Similarly, A and B and C weighting and all, what they will subtract for a given frequency is given here. That is this network, electronic network, what we have under the weighting network. This electronic unit, it will sense the frequency, accordingly it will subtract the value, and the remaining value goes there further. So next it goes to amplifier, output amplifier, and then it can either go to indicating meter where we have the reading, so many decibel we may have, or we can also take the output of the output amplifier for analysis, especially in machines and equipments where we want to locate the, because an equipment or instrument is made up of hundreds of parts, and which part makes the noise, maximum noise, we would like to locate. If you locate that part, then probably we will change it to another part making less noise. So for such purposes we have to analyze that signal, or for the frequency analysis. Yeah, it is done with the help of a octave band analyzer. It's called octave band analyzer. What it does, octave band means it will have band pass filter. It will have a set of octave, for example, octave band analyzer will have a set of band pass filter. Center frequency of each band pass filter, subsequent band pass filters will have a ratio of 2. That is why it is called octave band pass filter. Center frequency of subsequent band pass filter will have a ratio of 2. So you select one band pass filter, measure that SPL value. For that, for analysis purpose, you have to use flat, under the flat, because if you put flat, the weighting network will not do any subtraction. It will pass the SPL value as it is without any subtraction. That is why it is called flat. Under flat condition, we have to analyze. So band pass filter, so you select one band pass filter with certain center frequency, find the value of SPL, and then switch over to the next band pass filter having a ratio of 2 center frequency, and again measure the SPL value, and then plot it. For example, I got a plot of for the blower, electrical motor, how much noise it has made. Is plot of SPL, or I will simply write SPL of a blower, measured value. So here it is 63 hertz, one center frequency, other center frequency 125, then 250, like that it goes 250, 500, so 1000, 2000. That is how the center frequency goes. And here we have got 40 decibel, 40, 50, 60, 70, 80, 90. So from 75 onwards it goes. So 125 maximum. So 75. So it goes like that. So this is the plot of the different center frequency. You got this plot. So from here we know that at 125 hertz it produces the maximum noise. Probably 125 hertz may be a rotating speed of a gear machine. Then we find one of the two gear machines, one of the two gear machine gears, we change it to, if they are metallic, we can change it to say one plastic gear. One plastic gear machine with metallic gear will make very less noise. Then after making that again measure, then you will find this will go away. Like that we effect improvement in reducing noise in many equipment. So for that purpose we can analyze this signal also. Now we will see how the microphone functions. We have seen in the sound level meter, microphone transduces the sound or pressure variation into voltage variation. How this is obtained? We will see one version, that is the capacitor type. This is a capacitor type microphone. Here for example, we have for a capacitor we have got two plates. Whenever we change the distance between the two plates, the capacitance varies. That can be made use of in suitable electrical circuit, and we can get corresponding voltage signal. That is what is the principle used here. The capacitor is made up of the diaphragm on which the sound pressure is falling, sound is acting or impinges on that surface, and so depending upon the compression rarefaction, the diaphragm moves to and from, vibrates. That is that constitutes the moving plate. Diaphragm is the moving plate. Diaphragm is of the order of a micron thickness, metallic diaphragm fixed over the edges around circumference. It's circular diaphragm. Below that we have got so called fixed plate. It's also a metallic piece with the damping holes, because when the diaphragm vibrates at high frequency, if it is allowed, the diaphragm may break. So to avoid the amplitude of, to control the amplitude of vibrations, some damping is produced by having damping holes in the fixed plate like this, damping holes. What happens when the diaphragm comes down, it compresses the air molecule and makes them to flow through this restricted path, thereby some damping force is created, and the amplitude of vibration is controlled. So controlled vibration is there in the diaphragm. That is also achieved by having a capillary leak here. Capillary leaks, atmospheric pressure, this atmospheric pressure, the average atmospheric pressure will always find its place below the diaphragm. Otherwise, the diaphragm may also break. And also, when we want to have what is the pressure variation due to sound over and above atmospheric conditions, atmospheric pressure, we should have the atmospheric pressure here and here. So that is how the atmospheric pressure also is taken here through a capillary tube, capillary piping, capillary tubing. So now this is a capacitor where the distance is varied due to the vibration of the diaphragm, and you find with a insulator these two are separated, these two plates are separated, and the center piece as well as the housing outside, where the housing, it is metallic housing, where the diaphragm is fixed, is connected to a battery under resistance R. So it forms a full circuit. With a capacitor it forms a full circuit, a simple circuit with a single capacitor with a constant resistance. So whenever the gap changes, capacitance changes, there is a current flow to and fro, and then that current flow through constant resistor gives rise to voltage drop of EO. Now whatever the pressure variation, same variation is around that will take place in EO also. That means we have converted the pressure variation into a voltage variation. This is a capacitor type. In another one, piezoelectric type microphone. Yeah, piezoelectric microphone. There, piezoelectric crystal, for example, quartz is just put below the diaphragm. Whenever the pressure is varying, the quartz crystal it's compressed, and then you will find a charge is produced. That charge is amplified in a charge amplifier. Then you have the voltage output. That will be varying same way as the pressure variations. That also is available in the market. Yeah. That is, with the diaphragm we convert the pressure variation into force. That force acting over the crystal will produce a deformation in the crystal, and that produces charge amplified in charge amplifier. We get the voltage output. These are the two principles for the converting the pressure variation into sound pressure variation into voltage variation. Now when we want to measure the noise, what are the precautions? We are not the precautions are given by the manufacturer from whom we purchase the sound level meter. He will say don't hold the sound level meter like this, because for suppose source is there, it measures this directly noise from the source, as well as the source sound reflected from the body also may be picked up by the sound level meter. So he will always say hold the sound level meter by extended arm, that pointing towards the source. It should be suppose mic is here, it should pointing towards the source. So we should hold like that only, and at a particular distance, because distance decides the amount of pressure variations. If we go double the distance, pressure variation is reduced to half the. So in all measurements of sound, we are supposed to measure the distance at which we are supposed to quote the distance at which sound is measured. That's one thing. Secondly, I was telling there should not be any nearby wall and all. That will be taken care of if we are using the method of using anechoic chamber. Anechoic chamber is one where inside inside the room or the chamber there is particular construction to avoid any sound reflection of noise. That is, suppose there is a chamber, it has got 6 walls, bottom, top and 4 side walls. All the 6 walls should be filled with the so called wedges made from sound absorbing material. So whenever sound is made by a source, suppose this is a source, sound is going, and since it is a wedge, it gets reflected within the wedge formation once or twice, and it gets absorbed within that 1 or 2 reflection gets fully absorbed, and nothing more can come out to be picked up by the sound level meter. So the sound level meter will measure only the sound produced by the source alone, it will measure, no reflected sound will be coming here. But normally the size of such anechoic chamber is sufficiently big, because we should have a door opening to put to our source as well as instrument, having electrical connection and all. Providing all these things, it works out to be a big chamber, and any laboratory you should have a sufficient space. Otherwise this will occupy a big space, and after making one project and until next project after few years you may not be able to keep it there and you may destroy it. So there is second method, if you cannot, and also if you want to purchase it is costly one also. Second method is by making background noise also we can measure the noise made by the device. That is, now you have to make 2 measurements with the sound level meter. Suppose source is there making noise, and surrounding also will make noise. So you make one measurement called total noise, one measurement, where the source is running, also atmospheric noise also is there, total. Now you switch off the source, so it is a running machine, you know. So you switch off the power supply, so the source will stop, no noise, so you will be measuring the background noise. So you measure the total noise, and then after switching off measure the background noise. From these 2 measurements you can obtain the source measurement by using this equation 1. Equation 2 is obtained from 1 only. So but it is in terms of our required quantity, we want to measure the source noise, so you can use it. Suppose you have 2 machines, identical machines, assuming background noise is 0, if you want to measure the total noise, then you can use this equation 1, total noise equal to L machine 1 and L S is machine 2. So LM1 and LM2 you can put like that, and then get the total noise. For that, in such instance you can use the first one. So suppose 2 machines making same noise, then you will find total noise will be increased by 2 machines, 2 identical machines, total noise, that is total noise from 2 identical machines will be more by 3 decibels, suppose 3 decibels. Suppose each machine is making say 65, each machine making 65 decibel, that is machine 1 and machine 2 make 60, then total noise will be 68 decibels. 68, that you can check in this equation also. The identical machines making same decibel, if they are put together, total noise will be only 68 decibel, it is increased by 3 decibels. That you can check in this equation. That is the way, that is easier way of making measurements of noise instead of the anechoic chamber, which is costlier. But you should have a control over the background noise, that is sometimes very tough. That is why in our laboratory, when we want to make such noises, such noise measurements, we come at midnight, so that around there will be less noise, only noise from the birds and the wind may be there, but it may be more or less constant, and then we make measurements. So you have to select suitable timing to make such measurements. So with this we will complete this the sound measurements. Now we go to the flow measurement. Next topic, flow measurement. This is also one of the important process parameters. We are seeing now process parameters. First we started temperature. In process and chemical industries, temperature, pressure, and then flow. These are the 3 important measurements. Any process or fertilizer industries, chemical industries, these are the 3 important measurements. Plus flow is to be controlled precisely to get the required quantities of any product. For that there are many methods. We are not going to see all the methods. For example, obstruction type flow meter, there is a pipe, and you put a obstruction type flow meter. So, in obstruction, this is obstruction, and this is a flow direction. This is here when it flows, it will be flowing like this. We measure the upstream pressure and the low stream pressure at vena contractor, and then measure with the help of the manometer, and these are what we normally learn under hydraulics, and all the positive type flow meters are there to make the measurements. So, all those things I am not going to do it, only few other special methods used for flow measurements alone we are going to see under this topic, mechanical measurements. First and foremost, we are taking the pitot tube. Pitot tube is very often used to locate the to find out the velocity of the flow at any point. So, you can insert it at different heights, so that you can get the velocity distribution inside the pipe. Suppose this is the pipe cross section, and that pipe velocity may be varying like this. This may be the velocity at boundary layer, velocity will be 0 velocity. At the middle, it will have maximum, this parabolic distribution of velocity in any cross line cross section of a pipe. So, once you get this velocity distribution, and you can get later on average velocity, you can find out average velocity for this cross section, and average velocity, this is average, V average times the cross section of the piping will give you the total flow in the pipe, flow rate in the pipe. So, for that you can use the pitot tube also. What is the principal function of pitot tube? What you are going to see? We have got so called stagnation point, that is it is a tubing like this. We have got at center point one tubing, and annular another space is there, where the opening is made to the flow. Say at the 4 times distance from this tip end, we have to diameter of this support, we have to provide holes for the state. This is here only static pressure will enter. So, here at the stagnation point, both the velocity head as well as static pressure will be available here, because velocity also becomes 0, pressure is static pressure already there. So, total pressure Pt by gamma is the specific weight of this gas or liquid, whatever it flows. Pt by gamma, that pressure head, is equal to Ps static pressure by gamma plus V squared over V is the velocity of the flow, V squared over 2g. So, this is the total head available at the stagnation point, that is taken through a tubing to the manometer, where you have got a mercury manometer is available. The other limb of the manometer is connected to the static pressure. This is the static pressure. So, we have to ensure it is only static pressure is there. For that, you should see this axis of this pitot tube and the flow direction coincides. Otherwise, suppose it is tilted somewhat like this, I have shown exaggerated. Suppose it is tilted, then you will find through this hole some of the velocity head also will enter. So, static head shown by this pitot tube will be larger once there is a tilting. This angle is called A angle. A angle should be 0 for correct measurement. That is angle between the pitot tube axis and the flow direction is called A angle, and that should be 0. So, when 0 means only the static pressure alone will come here, that is shown here. The difference between these two things, static pressure and this, you will get the V square over 2g, that is Pt minus Ps by gamma got on this side, we got this V squared over 2g into gamma. And now the pressure difference in these two limbs is also given by Pt minus Ps equal to W into H. W is the specific weight of the mercury. So, the pressure, comparing these two equations, you can find V is equal, that is velocity is equal to 2g W H by gamma. Gamma is mercury specific heat, gamma is the specific weight of the flow. Gamma by G also you can say rho, the density of the flow medium, both are same. So, by this we can get the velocity at any given point, and later on we can find out the total flow rate in this medium. The one problem here is the error source is at this cross section, if you compare these two cross sections, you find in this cross section this much area is occupied by this pitot tube. Naturally, the flow in this section, flow velocity will be more, than this cross section. That means when total height remains same, flow velocity increases, the Ps this static pressure here will be smaller than the static pressure, undisturbed static pressure. That is called something like loading effect. Process of measurements disturb the parameters of measurement. So, to avoid it, what is done is there is another thing. This is a support side of the pitot tube. It also obstructs the flow. Obstructs the flow means the static pressure increase. By suitable distance of this limb to the hole, you will find the pressure drop, static pressure drop, and the pressure rise both can match equally, and then you can nullify that effect. But a proper dimensioning is important. That is this error source which can be accommodated, which can be properly thought, and then it can be nullified. But these are some of the error sources. Next method we are seeing is hot wire anemometer. The construction of hot wire anemometer is somewhat like this. So, this is the support. So, there is a wire, very thin wire of few microns diameter for about few mm, 1 or 2 mm length fixed there in the support. So, whenever the flow is there, the heat is dissipated from the wire to the flowing medium. So, this is the wire, its resistance changes, resistance is changing depending upon the flow velocity. So, that resistance forms part of a 4-arm bridge, Wheatstone bridge, and where each other arm will be of the same order of the 1 ohm. So, then output impedance, we know, we have learnt already, will be order of 1 ohm, and this is excitation voltage for the bridge, and the resistance series will be of the order of 2 kilo ohm. So, naturally you will find the current flow through the whole circuit is controlled by the adjustment of the series resistance R4, because it is of order of 2 kilo ohm. The whole resistance gives an equivalent resistance only 1 ohm. So, the current can be controlled by this. This is the construction of a hot wire anemometer. Yeah. What is equation, governing equation for this heat dissipation? I squared RW, I is the current flow through this wire, exposed wire, that this wire RW equal to H into A into TW minus TF, where H is the heat transfer coefficient, film coefficient of heat transfer in watt per or joule per second per degree centigrade per meter square. So, into area of the surface area of this wire, surface area of the wire, into difference between the this is flow temperature, gas flow temperature, and minus TF is the temperature of the, TF is the wire temperature is the TW, flow temperature is TF, because from higher temperature to lower temperature the heat flows. So, the wire will be at high temperature. When we switch on the power supply to the network, bridge network, they get, due to current flow, temperature is raised to a high level, and from there the heat is dissipated to the flowing fluid. This is the governing equation for this. Now, H is a function of velocity, I told, when higher flow means higher heat will be transferred. So, that is governed by this H equal to C1 plus C2, where C1 and C2 are constants into root V, C2 into root V. So, incorporating this equation in here and obtaining this equation, I squared RW is equal to, now this is in terms of H. Now, this equations indicates two mode of operation. One mode is called constant current mode of operation. Under that, I squared is constant. So, when V is changed, TW wire is changed. When I is kept constant, for increased velocity, TW has to come down. Yeah, that is the constant current mode of operation. In that, and another one is constant temperature mode of operation. That is, wire temperature is always kept constant. Whenever the flow increases, to maintain the wire temperature, I is increased, because when the flow is increased, naturally the wire temperature will come down, because larger heat is taken. To bring it back, you have to send more current. That is the second mode of operation, that is called the constant temperature mode of operation, that is constant temperature mode of operation. These are the two mode of operation in which the hot wire anemometer is made use of. Now, the calibration procedure is as follows. First, keep the hot wire anemometer in still gas, that is 0 velocity, and adjust the value of R4 so that maximum current can flow through the wire, so that it does not burn out. So, under that you got under that condition, whatever the current flow in through the galvanometer, that is imbalance current. So, when there is 0 velocity means no heat is taken out practically, that means it will assume maximum temperature and hence maximum resistance also. So, maximum imbalance, and then you will have the higher current. This is the for 0 velocity, the what is the current flow through the galvanometer. Then send then gas at known velocities. So that is for V1, that is for V1, this for V2. For known velocity, find out the imbalance current in the imbalance current flow through the galvanometer. So it is, we call it constant current mode because once we adjusted this, later on current through this cannot be changed. That the current flow through the circuit is controlled only by adjustment of R4. Once that is adjusted for the maximum current flow, later on we are not touching. Current flow more or less remains same. So the due to RW changes, imbalance current is changing. That's what we are making use of here to plot it for known velocities, and for any unknown velocity we can find out the current for any unknown velocity. From the current we can get it, we can get the velocity. That is the constant current mode of operation. In constant temperature mode of operation, the equation, same equation 1 can be written like this, and you will find I squared is equal to C3 plus C4, where all these things, because TW is going to remain constant, that is constant temperature. So you will find C3 C4 into root V. So is O is equal to M, O is equal to Mx plus C format, that is root V. So having root V as x axis, I squared as y axis, then you will find it is a linear relation. Again here also the calibration is similar, that is we still have the gas, adjust the current flow to the have the maximum, and find out the current flow through the RW, that is this meter current you have to take, you have to note down, that is the current flow for 0 velocity. Then different velocities gas will be flowing, and adjust the R4 for another one, another velocity, adjust R4 so that the G will be brought back to 0, but what is the current flow through this you can find out, when necessary current flow through this. To bring the balance back, what is the current flow that you can find out, that is I1 for velocity 1, similarly I2. So you plot this curve for the current through the RW, and for any unknown velocities from I squared, from I measurement you can get the I squared, then to get the root V, from that V we can find out. So you find the constant temperature mode of operation, we have to make adjustments for, because current we have to change, that is manual. So the constant temperature mode of operation can be used for only static measurements, whereas constant current mode of operation can be used for static and dynamic. But switching over to automatic bridge balancing, we can use this constant temperature mode of operation even for dynamic measurement also. That is done like this. That is the RW by air temperature. So to start with, R3 is made larger than R4. And again same procedure, at 0 velocity of the gas, you fill it up, and then you switch on. Immediately you know R3 is larger than R4, so immediately imbalance will be there. That imbalance voltage will be amplified, and the current will be sent back, so that RW is brought near about R3. Whatever is the current flow required to bring RW to R3, and that flow through capital R, constant resistance, gives rise to voltage output E. So for 0 velocity, what is the current required? Similarly for any other velocities, what is the current required to bring the RW to near about R3? That will be current flow through this, and by plotting similar curves we can find out. Say for EO versus velocity, velocities we can have somewhat like this, and then from the for any unknown velocity, from the measured voltage we can get back the velocity of the fluid.